Hi, my name is Henry. In this video, I'm going to present the NRL project. I will start by providing a general overview where I'm going to explain the motivation behind NRL. Next, I will discuss how you can include NRL in your project. In the last part of the video, I will explain how to compile the project and how to run the demonstration programs. Please stay with me. NRL is a program developed for neurocognitive behavior control. Thus, it is assumed that your project counts on either a virtual or a real robot. The robot sensory system must also be capable of providing you with estimates of its state. That is, a posture for articulated robots such as humanoids and manipulators. NRL takes as input temporarily contiguous observations of the robot's state and produces a desired output to be executed by the robot's control system. The mathematical description of the record neural network can be consulted in the papers and the project's documentation. Computations for real-time interaction experiments must be efficient. For this, NRL is implemented in the C++ programming language. However, as a compiled language, C++ is not very efficient for quickly prototyping. Also, some interpreted languages, such as Python version 3, include several graphical and statistical tools that could be very useful to experimental research. For this, we propose two ways in which you could include NRL in your project. As shown in the figure, you could include NRL as a C++ standalone program. Alternatively, you could compile NRL as a shared library and wrap it around a Python class. There is, though, a loss in performance estimated to be around 30% when including NRL as a shared library in your Python project. So the final decision would also depend on the desired control loop frequency for your project. Please download the Eigentemplate library for linear algebra. We have tested the version 3.3.0 for demonstration in this video. It is required an implementation of the C++ standard library. I am going to show how to compile the programs in Ubuntu version 16.04, since it is a free platform. Ubuntu is delivered with the GNU project implementation of the standard library. The compilation tool that we recommend to build NRL is CMake. Please look for how to install CMake in your platform. I have downloaded the project already in this folder, so let's take a look what is inside. I recommend you to consult the documentation by opening this file documentation.html in your browser. You will be provided with an overview of the project, including important descriptions about its functioning modes and also the requirements, detailed instructions complementing this video, and also with some metrics or performance report on a reference machine and for you to compare with your local resources. NRL takes a property file into account which contains the parameters required to perform the experiment. So here you have a detailed description about the meaning of these parameters. I invite you to take a look at this resource. You can also browse through classes, and let's take for example the libNRL class. So it provides you a full object-oriented description of the methods, the meaning of the parameters, etc., the functions involved, and the calls that this method makes. Please take a look at this. Now I am going to show you how to build a standalone program. So firstly, as I explained before, we need the eigen library, so I have already downloaded here, and we have to say to CMake where to find these sources, which I'm going to show you now. So our standalone program is located in the folder named Standalone, basically this main.cpp file. CMake takes CMake lists information into account. We have to edit this file, and just in this line where it says include directory, we have to substitute the default text by the full path to the eigen library. We save this file and we are good to go. Now we open the terminal, and let's say we want to build the standalone program in a folder named build. So let's create it. Now we have to say CMake where to find the cmakelist.txt file. CMake NRL sources standalone, and it will configure the building environment. I'm going for building the program. We just have to type make and hit enter. I am going to pause the video because it's going to take like a minute or something. Good. So now we have our program built, and now the second step is to edit the property files in order to say explicitly where the resources are in our machine. So for this, we go to this data folder, and we see that there is a config folder that contains 3 different property files. So these are just 3 demonstrations for a Cartesian, a generic, or a robot type robo. We're going to be demonstrating the Cartesian robot. So we edit this file, and as we can see, we are required to pass the full path to this data folder, right? So let's going to do it. So this is the parent of the data folder. We just copy this and add it here. Got mistaken. Okay, so we have to do something similar for the model path. This attribute just says where to save the model data, and eventually if we want to run an already trained model, then it will load this model from this path. So let's create here a folder named model, and then we will call it Cartesian. This folder doesn't exist, so let's create it here. We create model and Cartesian. Good. So we are now all set. Let's go back to the terminal screen, and let's just run this program. So now this program takes 2 arguments. So the first argument is the full path to the property file, right, in this config folder. So let's do it. And now the second argument is of 2 kinds, either to train, so the word train, or sim for simulation, which will be simulating a real experiment. So let's first train. I am going to pause the video because it will take some time, and then I'll come back to you once it's finished. you should get an output like this. So the demonstration considers training for 1000 epochs, and probably these figures about the time is going to be slightly different as reported in the library documentation, because I am using a different machine for recording this video. So now we are ready to execute the interaction, let's say simulation computation, right? So we just use the keyword sim, as I said before. Under the selected circumstances, which you can consult in the main.cpp file, in this machine, the calculation loop, the computation are estimated to be around 57 milliseconds. Let's take a closer look to the demonstration program, so we can discuss scenarios related to your project. So everything starts by loading a model, and then basically some verifications, but the interesting parts, they come here. So the idea is that basically this is the experimental loop. So time is measured before NRL performance computations, and this command here suggests you to take into account the fact that here you should read data from your robot, right? So this is the current position or posture, let's say, of the robot, and then you should here call your driver and get this data in this vector or in this array. Then NRL is called to generate a desired posture, which is the target posture of the robot, and here you should call asynchronously your driver in order to send or to request it to execute this posture, right? And while continue to operate in this segment of the loop, there is the process of inference, and then, as you can see, the current observed posture is appended to a temporal buffer, right? So just basically this data is passed to NRL, and it changes the internal state of the neural network. You could save this data and analyze it later. So this function getState is very useful for this. So here you should consider, for instance, appending this model state to some kind of data container, and at the end of the algorithm, then you just persist this to hard drive, for instance. The structure is very simple, just like 5 or 6 method calls. Hopefully with the commands you will get the meaning and the purpose of this demonstration. For building the shared library demo wrapped in the Python program, we have to proceed analogously. But there is a small difference. Now, instead of this folder, we will consider the lib folder, where there is this CMake list file. So we just edit it, we save the file, and that's it. So now we go. So now I am going to show you by default how this is configured. So if we go to this folder Python, you will see a main.py file and an NRL.py file with just wraps. Maybe we could observe what's inside. So basically what it does is to include something inside a folder named lib. For Windows or Mac OS or Windows, it may have different extension names. So, but it's assumed by default that it's here in the lib folder. So you can change this path if you want, but let's stay with the default thing. So we're going to build our shared library in this folder named lib. And now for this we go to the terminal again. And okay, so we just repeat the procedure. So CMake, it is in the source lib file. Okay. Since it's going to take a while, I am going to pause the video and come back to you once it's is finished. Here we are. So we have our library build. Now we just have to call the main script, and as before we provided the full path to the property file. So this model, I'm going to use the Cartesian model. We just trained it, we simulated a training with a standalone program, so it already saved the weights and biases of the neural network. I'm going to use the same. Yeah, so here we have our simulation performed, and as you can see, the time is slightly higher in comparison with the standalone program, which is something that you have to consider when choosing one or the other. Thank you very much for watching this video. I would like to suggest that you take a look at the VCBot project, where NRL is included as a shared library in the Python programming language, so you can interact in real time with a virtual Cartesian robot through the computer mouse.